Alright, so let's try to solve day 23 in Nim. So day 23 is called LAN party, and I can already tell that it's a graph problem, maybe because of how the input looks like and also because of LAN party. So we have a list of every connection between two computers. Obviously it's a graph problem. Let's see what we need to find. So each line in the network represents a single connection. This line represents a connection between computer name KH and the computer TC. And the connections are unidirectional. That's, I guess it makes sense. And we need to try all the groups of connected computers. So we start by looking for sets of 3 computers, where each computer in the set is connected to the other 2 computers. In this case, we have 3 of them, and I'm pretty sure AQ appears twice. So it's, let's say this is a group of 6 computers that are connected. Oh, maybe they are not connected in between each other, but AQ is just connected to 2 of them. Right, and then to the other 2 of them. Okay, makes sense. Maybe that's okay. So I was thinking, well, do we need some kind of detecting all the fully connected groups? I don't think so, because AQ, like, oh, we'll do a drawing, but yeah. Okay, and here we need to consider only the groups that start with a T. So TA, TD, TC. Okay, how many contain at least one computer with a name that starts with T? So we need to find all the groups of 3. Okay, so if we think about, we could just have 3 for loops, and just generate all the permutations. So that's a thing. We can generate all the permutations and see if they are actually connected. But I'm scared about part 2 anyway. We can try that, like, why not? And for today's language, I was thinking of using Nim, because I think it's a decent language I can try. I know, I mean, this one just as Groovy and Kotlin, and actually a lot of other languages I know absolutely nothing about, so I don't even know the syntax. I just copy pasted some example of reading the input, so I think I have a make file. Yeah, and I also collected some like, let's say, cheat sheet.md for this language, just in case we need some quick stuff. Called it tmp.md, although it looks a bit weird anyway. So if I run make, it's like really weird, the compiler, but anyway, hopefully it's not gonna be anything weird. Okay, so we actually read the input. That's great. That's great news. So yeah, like what I said is, let's imagine we have, this is a node, let's call it, let's do the AQ one. AQ, that's a Q, trust me. And then we have CG here, YN, and they are connected. And then on the other side we have the other 2 nodes, and you can see that it's not necessarily a fully connected component, but it's like this is one and this is the other one. So yeah, doing 3 loops, why not? Let's just do 3 loops. So let's try to have a function. Let's cheat. Let's see the cheat sheet. So I would like to define a function so I can see it's using proc. Proc. Okay, I mean, maybe we can find nim docs. All right, so let's try to solve now part one using nim. So basically, we need to start with the parse input function, right? That's the first step usually. So let's I'd like to use this learn name in y minutes because I don't know why I didn't think about it from the beginning. It's a pretty good option, like for each day almost. When you use a new language, like this should have been like the classical cheat sheet. So yeah, let's start with making a proc for the puzzle. So parse input is basically a string, and we want to return, let's say I want to make a hash table. So for that I need to import std.tables or something, tables, and we have table in here. Not really, but we know how to define a table. It's table, and it's gonna be from, we are gonna try to build the hash map that goes from one node to all the neighbors, let's say. So we're gonna have a sequence of string. Okay, so I think we'll need, it's like table, right? Import string strutil or something. String split name. I think it was strutils or something. Oh my God, that blinded me the fuck. Okay, so here is gonna be input dot strip, so we remove all the new lines at the end, then we split, let's say, by a new line. So this should give us all of the lines, right? Makes sense. Then we can maybe even map this thing. But how can we name sequence map? I can see it's used like this. Okay, so we try to map this thing with the procedure. It takes in a string and it should return, actually, let's say it returns a tuple, string. And almost had an idea, but so this should be something like let vertices is equal to line that's split by a minus symbol, like dash, and then we want to return vertices 0, vertices 1. Alright, so this thing, how does it look the best, like this or no? But this is not the right type. I should just test with TMP. Oh, import secutors. Yeah, it's secutors. Yeah, but it expects table and we return just a sequence of tuples, right? So how are we gonna convert this? So here we get the edges basically. So let edges, we get the edges of our graph. So we want to build, we want to go from edges to the like adjacency graph. Is it called like that? So something like edges to adjacency graph. Converting between, I'm curious, is it like a straightforward algorithm? So we have basically this thing, but I don't want adjacency matrix. I want hash table. Alright, something, I mean, adjacency list. Yeah, whatever. Let's try to figure that one by ourselves. I wanted to see what's it called, but I don't know. So the idea is, so we have a list of the edges and we want to just build this hash table. So let's say we have, let's say we want to find something like fold left or something. Right, so we have fold left. We can use fold. So we have the sequence, which is the edges. We'll have proc. Wait, what the fuck is? Huh. I mean, we'll have a proc. Hopefully it works with the proc. Whatever. So we'll do like a proc maybe. And the initial value should be new table, and the type is gonna be string secu string. I think that's kind of inferred, but so this is okay. I mean, name fold left example. Can we see an example? Yeah, but that's what's a times b here? Ah, it's a template. What the fuck is this shit? It's a template. Oh, I get it. Where a and b are the operands, but which one is the accumulator? I mean, honestly, no, let's not use fold left. Like, what the fuck? I thought that it's gonna be like, so anyway, so let's call them connections. New table, string, sequence. I mean, we can convert it to a functional style later, but I thought that it's gonna be like edge in edges. Okay, so edge is can I iterate over a sequence? I mean, would be cool, but so can I do a for loop over a sequence? Like, yeah, I guess so. I guess so. Looks like it also returns the index though. Yeah, see, it works. So can I do something like A, B? And A is gonna be just this. Yeah, nice. So it's really like Python in a weird way. Okay, so connections of A is connections get or default get or default A or an empty list. And can I just say plus B, I guess? I have to put a at shit concat. Wait, really? Oh, that. Oh, this is concat. Nice. You learn something new. So in the end, this is just connections. We got table ref. But expected table. Wait, why is it table ref when I said new table? New can I say like to table? Name got table ref expected table. Like someone must have run into this one. But if I declare it as let, it's gonna complain that still complains about that dumbass table ref thingy. Oh, I mean, it doesn't help at all, this error message. Got table ref when I literally say new table, but it is what it is. So this is table ref. New table. I mean, we already have a table here, so how do I create a table, init table. Oh, it's init table. I mean, that's crazy, though. Okay, perfect. So now it compiles at least. So can we say let connections is equal to parse input, and maybe even print this thingy. Yo, we actually could. That's nice. So what do we want here is, so we basically have let's call it the topology of the network, right? For each node we know how it's connected. So maybe the other thing we need to do, just not forget, is to make it bidirectional by doing this. So now it should be bidirectional, right? If we add both of the edges here. Okay, anyway, so let's try to solve part one. So for part one, what I'm thinking is this thing is gonna get the connections. So table string and CQ string, and we should be able to do a for loop like this. So for computer and neighbors in connections. What is computer gonna be? It's a string, and neighbors is gonna be nice. So it's really like a really Python thing. So it's gonna return an integer. Let's say counter is 0, and at the end we return the counter. So we know that computer is the one that we want to check. So for neighbor in neighbors, this is the second computer in the chain, and we need a third one. And initially, I tried to do 3 for loops, but that's like 3 sum. Whoa, that's like the 3 sum problem. If you don't know 3 sum problem, it's trying to figure out 3 numbers that summed up, you get a sum. And to make it more efficient, you have to use a hash map. So that's kind of what we have here. So this is the first item, the second item, and to get a third item we need to use a hash map here. So how can we do that? Well, we know that the third computer should be either in neighbors or in connections of neighbor. So it's in one of these lists. So can we have an intersection? Oh my god, I almost shit myself. Okay, so here is nim seq intersection. I guess nope. So what we are gonna do, I guess set is a good idea, is a good approach. What the fuck is this operator? Oh, that's intersection, right? No, that's difference or something. Intersection. Nice, so we have intersection, perfect. So, but for this one we need import sets. So we could import sets and we can try to do this thing. So I'm gonna do to hash set neighbors and to hash set connections of the neighbor. So again, if you think about it, we have our first computer is linked to these other computers, and this second computer is linked to these computers. So if we take the intersection, we get the computers that both of them are linked to. So we have to say for other in intersection of these two. Oh shit. Other is a string, neighbor is a string. So basically if computer starts with, well, you know what, counter, let's see if we get the, so how many, let result one is part one of connections. So for it's 12 3 interconnected, right? But I get 70 fucking 2 because they need to be different. So if computer is not equal to neighbor and neighbor is not equal to other, they also need to be different. Wait, what? What? So here we get all the computers, we get all the neighbors. Let's put like some spaces between them. Wait, that's weird. So I'm pretty sure there are gonna be like duplicates or something. I guess no. That's weird. I ran it on TMP, right? Yeah. Code. Wait, what? Yeah, see, it repeats itself. So I mean the easiest way to get rid of that is to maybe have a var visited init hash set, and it's gonna be a hash set of wait, it's gonna be a hash set of hash sets. Is that weird? Right? Because what's gonna happen here is visited insert append. How do I put something into this thing? Push. Wait, what? uh insert. Wait. Nim hash set insert item. What? Include? Okay, a really weird name for it, but it is what it is. So init hash set. Can I just actually to hash set, and here we are gonna put the computer, the neighbor, and the third party basically. So we include all of these, and let's say trio. Let trio is this thing. So these are the guys that are playing. Has contains. If visited contains trio, then we don't do anything. But if not, then we do all of these for now. Right, so that's gonna be the thingy. So we keep this visited. So now we get 12, which is the initial answer. But we need to discard everything that doesn't start with TA. Right, so it's I'm just gonna make a function starts with T, and we are gonna pass in let's try to use a hash set of string, and we'll return a boolean. So can I just say all inside of trio like s is a string and returns a boolean, s dot starts with, and it's more like any of them start with T. Right, and here I can say and starts with T trio. But maybe it doesn't work on, so it wants to be an array. So can I say something like to sequence? Should be like the first function. Yeah. Okay, so maybe I can say sequence. Interesting. 7. Nice. So we actually get almost 1200. And surprisingly enough, that's actually the right answer. That's nice. Right, so let's see what part 2 is about. So there are still too many results to go through. We'll have to find the LAN party another way. Okay, so since there are no employees around, we figured out there must be all at the LAN party. We need the largest set of computers that are connected to each other. That is, for each computer, the people running, so in this example, the password would be, wait, the LAN party passwords to get into is the name of every computer sorted alphabetically, then joined together with commas. So we need to find the largest fully connected component, or it's not necessarily fully connected, it's largest set of compute. Yeah, it's actually the fully connected component. So that's a fully connected component. Finding the fully connected components, right? That's the algorithm that we need to solve. Click decision. Oh, it's the NP complete one. I mean, shouldn't be. Like there should be like an algorithm. Let me just turn on dark reader because it's blinding me. Right, so maybe what do we need is, let's make the drawing. Wait, what did I do? So let's imagine we have, this is a node, this is another computer, and so on. So if we select, let's say we look at this one, let's say this is the starting point and this is connected to two computers. It means that, just remove that. It means that the maximum size, like of a small LAN section, is 2, because we have only two neighbors here. Let's say this one is connected to three of them, right? So when we take this as a starting point, we see, okay, this can have a maximum, like it has a potential of resulting in like 3 computers connected to each other. So what we can do is take its neighbors, right? We can take all of its neighbors. Oops. Can take the neighbors. And like for each neighbor we take their neighbors maybe and generate the intersection. So let's say this is A, B, C, D, and E or something. So let's say we start with C. So we take all of the neighbors, right? So we have like A, B, C, D. This is for D. And we intersect that with, let's say, neighbors of B. That's B, A, and C. I mean, neighbors of B and B itself, actually. Then for A, it's A, B, and C. It's like A and the neighbors. And D is D and C. So if we run the intersection, boof, we get only C. And that means that if we start at C, and we are trying to get a 4-sized click, we cannot do that because of D. But if we say, okay, let's start at C, but let's look for only a 3-sized one. So instead of looking also at D, we look only at A and B. So the intersection of that is going to be ABC, which is fine. So does that make sense then? So we have to iterate all of the vertices. Then we have to say, okay, the potential of this vertex is the number of neighbors. So the potential is going to be the number of neighbors. However, maybe that's not going to be exactly what we actually get as the size of the click, right? So maybe as for C, the potential is 4 because it's 4 neighbors, or I guess it's 3 neighbors plus itself, but the actual size is only 3. So we have to somehow go from the potential lower and lower until 1, for instance. But it's no point to go until 1. We are gonna have like the minimum number, which is the current maximum, right? So let's try to do that, and let me just delete the DFS thing that I tried before. So that's that. So we'll have visited. I don't even need visited. So let's have maximum component as size 0, and we'll keep track also of the largest component in a sequence. So we go over the computers, right? And what do we need to do? Let's say let potential is, actually let me just computer and like neighbors, neighbors. This is the potential result, right? So what we have to do is to go from potential to max component, right? So there's no point in checking lower than max component. So that's the idea. But we need a way to generate all of these combinations. I mean, that's right. We need the combinations of the neighbors. So let's see, can I for loop? I need a for loop, but I need a for loop to go from, I need a range but with negative direction, if you catch my idea. So it's gonna be something like from the fuck, there's no example. Nim for loop decreasing range. Okay, that's fucking useless. I'm gonna do like a while loop. So let's have while potential is greater than max component. Then we are gonna say potential minus 1, basically. Okay, so it needs to be a var. All right. So we need the selected neighbors. We need to somehow generate combination. Does Nim have combinations? Nim combinations. Doesn't really have it. Thank God. Okay, so that's what I want. I'm just gonna copy paste it because why not? Let's just copy paste it here. Hopefully it's just gonna work because I don't really care about how it's implemented. Discard. Wait, that's cool one. I mean, yeah, you know, it's combinations, whatever, who cares? Let's just try to get it. So we have choose, and we pass in the neighbors and potential. So this is gonna be our selected. Wait, what? So for selected in. So here we are gonna select some neighbors. All right, and the idea is so we did the following. We selected the neighbors, like combinations of them. So we need to do intersection of them. So how is that gonna work? So selected is a list of strings. So let's say var click. It's gonna be, or I guess, it's not really the click, it's more like the intersection, but it's click. I mean, in fact, it's a click if you think about it. So yeah. So what are we gonna intersect here? As I said here, if we selected C, we need to intersect the selected ones plus C. So initially the click is gonna be is gonna be selected plus C, right? So it's gonna be selected is the neighbors plus C. So that's my ideal case scenario. Initial one, this one, ABCD. So let's say hash init hash set. I guess to hash set is better. Select to hash set selected. Can I have like a name spread operator? Is that a thing? Name language splat. Nope. So select it to hash set, and can we just, no, I know a better way. Computer to hash set. Oh my god. So this one. Nim concat to sec. I mean, maybe I just need to put this. Nice. It actually makes sense using nim, to be honest. So that's our ideal case. And what do we need to do is for s in selected, we need to do something like click dot intersection. Oh, it's just multiplication. Holy shit. Click multiplied with s. I mean, multiplied with connections of s and s itself with hash set. So that's gonna do the intersection, and by the end of it we'll know if len of the click is greater than max component, then max component is len click, and largest component is max component to secu. Wait, what? But how is it? Click to secu. KD kota. Yo. Yo. Okay, how do we sort name? Sort sequence. That's what we need. How do we sort the sequence? Yo, sort. Largest component, and let's also echo it. What? System CMP. Dude. Like, this is so weird. Sort. This is the best page for Nim, to be honest. Sort. The one with the one here from learn X in Y minutes, and then it's this page, collections and algorithms. It's like completely one of the best ones. So okay, but why does it complain here? Hey, what the fuck? Okay, let's see the compiler. Maybe the compiler error is gonna be better. So we have a sequence string and like a procedure, whatever. Expected one of the ordered table. So I need to import something, but what the fuck do I need to import? Algorithm. GG. Easy. Well, that wasn't enough, apparently. Sort. It returns not. Okay, so it's in place. Echo a largest component. So it's in place. Codecate. Code kata. Okay, so join. Do we have a join? We have a join. Join with a separator being a string, so comma. And that should, okay, that's it. Nice. So echo result 2. So can I just say part, I mean, you know, we are already finished. We are just BMing at this point, part 2. I mean, we would have to make sure that it runs on day 23. I was expecting to see like a weird message, but boo, that's sad. Wait, it was just commas. Yeah, the people running, I mean, bunch of, lots of these freaking nerds. Okay, so, I mean, it looks right. Max component equals, is it like, ooh, we got another answer. Yeah. Let's think about it. Maybe we are making a change somehow. So why? So potential. What the fuck? Why does it matter if it's greater or equal? Why does it matter? Well, like imagine the following. Imagine that I mean, it's the same length though. Am I stupid? No, it's one more. No, but think about it. it needs to start with T. It doesn't, right? It's just the largest one. So let's imagine the following thing. Let's imagine that max component is 5 and our potential is also 5. You know why? Shit. The potential, yeah, you know why it's or equal? Because this is the number of neighbors and the max component is actually the number of neighbors plus the node itself. Okay, that was a neat bug actually. Yeah. Okay, so I mean that was a good one. Yeah, so if you didn't quite catch it, it's basically max component has, if you look here, we put selected and the computer. So they're both of them. But the potential, like the max potential, is the length of the neighbors, and the length of the neighbors is just selected. So here we are doing +1 on the potential basically, right? So that's the idea. And then here we say that the max component is the length of the click, but the click can be all the neighbors plus the computer, right? So yeah, that's kind of it. I mean, pretty cool. I mean, Nim doesn't have this one. I had to copy it, but it is what it is. Should be part of stdlib if you'd ask me, but yeah, quite interesting. Here I was just trying to do it in Python, like figuring out some things. So yeah, we actually got it. Nice. So I guess that's all for today with Nim. Pretty cool. Like it's Python-like in a weird way. It's like Python with types, if you think about it, because it's really Pythonic with these operators. Python has a lot of these weird operators that are just symbols, so that's kind of fun. So yeah, I guess that's it for today. We managed to solve day 23 in Nim, so that's kind of cool. So yeah, let's see in the next one.